So why is the sun so special for us? Here is a very basic comparison. Let's say that you took the sun and put it at a distance of 1 parsec, and then you took the biggest possible optical telescope, which would be a 10 meter wide Keck on Hawaii, or there are a few telescopes of that class, and you took a look at this sun 1 parsec away. It would look like a point to you. Actually, it wouldn't really look like a point to you. It would look like some sort of smudge because of the diffraction happening on the lens, or actually on the mirror of this kind of telescope. So you wouldn't be able to resolve any detail. So the size of the sun at that distance would be something like 0.004 arc seconds. The resolving power of such telescope at optical wavelengths would be 0.012 arc seconds. I'm going to go next week over the equations and the physics behind this, like why we can't see infinitely sharp, why we can't basically make infinitely sharp images even under ideal conditions. But this is basically what happens. So the fact that you see stars in the sky as little dots is not because of their finite size. Most of the stars that we see in the sky are basically dots, literally dots. And there is no spatial information contained there whatsoever. This is slowly changing now with better and better interferometric observations, but we still can apply them basically only to giants or very, very close stars. Okay. However, when we look at the sun, with the biggest telescope today, which before Dickies was Gregor at Tenerife, looking at the same wavelength, we can achieve worse resolving power, so something like 0.08 arc seconds, which, however, translates to roughly 60 kilometers at the surface of the sun. So, to make a comparison, the radius of the sun is 600,000 kilometers. And theoretically, if the atmosphere is collaborating with you, you can see details of the size of the 60 kilometers. So I really like this image here, and I'm going to zoom it now, and we're going to spend some time basically admiring it. So this is an image from another telescope. This is so-called Swedish Solar Tower at La Palma, and unofficially, or let's say in my opinion, it has been until now the maybe telescope producing the sharpest images, right? Of course, with Dickies we hope to surpass this. But take a look at the sharpness and the amount of detail that you see here. So for the comparison, one of these little granules here, and we're going to see a little bit later where these granules come from, has size of roughly 1,000 kilometers. So we see now in this image the structure of these granules in a great amount of detail. Of course, and then again, there is something else here, which is not a granule. This is actually a sunspot. And again, you see a lot of structure in this sunspot and various things happen. So there's a lot of information hiding in this one image. And of course, this one image wasn't just produced by pointing the telescope at any given moment and recording what the telescope saw. There was a lot of, let's say, lucky things like waiting for the atmosphere to have an appropriate condition and then using various image restoration techniques to get this. But once again, when you look at it, there's really a lot of things happening here. And there is no way that you would see anything close to this when you look at the other stars. And I mean, it would be really foolish to even try and extrapolate and say when we would be able to make these observations of the other stars. So for example, if you want to study the granulation, which is basically the convection in the atmosphere of the sun in any star directly, the only thing that you can really observe at the moment is the sun. And here we can really clearly see what is happening. And our goal today, not only today, during this semester, won't only be to try and see how to get these nice pictures and how to basically improve our data that we obtain on the ground to get these sort of big pictures. We will also be interested how to interpret these pictures, how to go from this nice image to obtaining some actually data, some temperatures, some magnetic fields, velocities, and other kinds of things. Some numbers that we can ultimately say, okay, this is the physics that happens, or this is the physics that happens, and so on and so on. Right. So, Of course, as you're guessing, the images won't suffice. We will have to obtain some spectra as well. We will have to measure some degrees of polarization as well, and so on and so on. And we're going to go slowly through all these things. And basically what I want to convince you today is exactly this, that images are not enough, that we need to do spectroscopy, that we need to do polarimetry, and very often we need to do the same. Or said in the other ways, we need to look at the sun at different wavelengths. Sometimes for some missions, especially for space missions, these are drastically different wavelengths. For ground-based observations, you can also combine, and you can exploit the fact that sometimes at some critical wavelengths, at some very interesting pieces of the spectra, changing your wavelength you're observing it by a small amounts carries a lot of information. All right. So what I also want to emphasize is that when we observe, we see the atmosphere directly. Okay, so we don't see anything else. And actually there is always one beautiful example of in stellar physics that I always sometimes find misleading, and we're going to spend some time and discuss it. I think it comes in the next slide. But I also first want to share with you this quote here. So does anybody here know who Edward Salpeter was? Salpeter was a stellar physicist, I think he worked in like the middle of 20th century, and he's famous by the so-called Salpeter initial mass function. So he basically he theoretically derived how stars should be distributed according to their mass, okay? And we use that even now to model how, for example, stars are distributed by mass in the galaxy. And Dmitry Michalis is also another giant of astrophysics who devoted his work mostly to the study of the stellar atmospheres. And apparently this disruption happened at some time. So Salpeter was this old school guy who was devoted to theoretical comparison, to calculation of stellar structure and so on, and the comparison to what we see and so on and so on. And he couldn't really appreciate why would anybody devote the time to study the atmosphere itself. Because he thought, okay, the energy is created in the core, eventually that energy is going to leave at the surface, we're going to measure that energy somehow, we're going to compare it to our models, voila, that's everything that we need to do. While Michalis actually said, okay, this is not enough, there are a lot of things happening in the atmosphere, we can probe these things by looking at the spectra, and spectra carry signatures of much, much more things. So let's devise some diagnostic methods and let's compare the calculated spectra to the observed ones to figure out what is happening here. And for us, or at least for me, it is also very simple why we study the atmosphere. It's because it's the only layer that we can directly observe. So when we look, let's say that we want to do some helioseismological study, we are looking at the perturbations that are happening in the envelope of the sun, but we are detecting these perturbations because the atmosphere is oscillating. Furthermore, these oscillations are excited through the granulation processes that are happening, let's say, on the borders between the envelope and the atmosphere. So it also gives us the insight into what is happening inside. And the misleading example that, okay, I'm going to share it with you a little bit later, but also, I mean, when it comes to, we will spend a big deal of the course actually discussing where do photons come from and what kind of information they carry with themselves. But let me already say that photons don't come directly from the core, okay? The only particles that come directly from the solar core to us are neutrinos. And that's the only direct probe into what's happening in the core of the sun. Okay, cool. So let's go very briefly about how the structure of the sun looks like, just to basically remind you. So we have the core, which is basically inner 25% in the radius. And roughly speaking, I'm sure that you've heard this many, many times, is that that we have two fusion processes competing. One of them is so-called PP chain, where you basically have two protons fusing to create the core of deuterium atom. If that happens 2 times, and each of these deuteriums fuses with another proton, you'll get 2 isotopes of helium, and these can finally fuse to produce the, let's say, regular helium, helium-4 that we usually think of, and return us 2 protons back. And there's some energy produced along the way, and that energy is produced as 2 gamma photons that you see here, and 2 neutrinos that you see here. So neutrinos more or less directly leave the core and leave the sun, while these gamma photons carry the energy very, very slowly toward the envelope and then toward the solar atmosphere, and finally the radiation escapes from the solar atmosphere and reaches our telescopes, and we measure the radiation properties, and so on, and so on. So basically the temperature in the core and the composition of the star are going to determine its luminosity. And that's already one application of the solar physics, is that we can measure the luminosity of the sun super precisely and its spectral distribution and so on, and it can serve as a sort of level 0 test for our models of stellar structure. And this plot here actually shows you how. Oh, okay, sorry, I didn't tell you about the other process. So there is another fusion process which directly competes with the PP chain. It's CNO cycle, and it's basically a process where you start from, let's say, a carbon atom and a proton, and then you have this cycle of fusions where you basically add additional protons on the way. You're going to finally end up with a carbon atom which you started with, but since you added 4 protons along the way, you're going to also end up with a helium atom. And on the way, there are going to be some gamma photons emitted and some neutrinos emitted. Okay? So these belong to stellar, stellar structure topics. So I just want you to know where the energy comes from. And for me, this plot was always very interesting. It's the plot that shows you basically the efficiency of these 2 processes depending on the temperature. Okay, and you see that their dependence on the temperature is different, and sun actually lies on a very interesting point where basically CNO cycles is a little bit more important, but not so much, right? So basically these 2 are roughly equally important in the solar core. Cool. Then we get to a big zone in the envelope of the star, of the sun, but also other similar stars, where the energy is transmitted by a radiation. And usually people like to illustrate that as photons are randomly scattering and leaving out. I don't really want to depict it as scattering. I more like to look at it as a chains of absorption and emission processes, because also the temperature changes in this region here, so the spectral distribution of the light is also going to change, right? And then eventually these radiative processes are not going to be efficient enough to carry the energy outward, and we're going to have another region where the energy is now transported with convective processes. And convection is something that you see almost every day whenever you're boiling something, is that the chunks of the material which are warm tend to plop up on the surface where the cold ones are falling down, so you get these sort of cyclical motions. So you're not moving individual photons or atoms or molecules or anything, you're moving big chunks of the material which are cooling as they climb up, and they are releasing the energy radiatively and that way transporting the energy outward. And we see some signatures of this convection on the surface of the sun as the granulation, okay? And here is basically a very simple, basic picture how the interior of the sun should look like, calculated from a model. So what we have here is the dependence of the pressure, temperature, and density on the radius looking from the core. And you can see, for example, that the pressure, which is basically proportional to the total amount of particles, in a way changes by 9 orders of magnitude when you go from the core to the outward. And basically, already 5 or 6 orders of magnitude happen in this last few percent, which you could say is the atmosphere, okay? For density, it's pretty much similar. Then we can also look how the luminosity and the mass of the sun change with the radius. And basically this will bring us naturally to the definition of the core. So you see that luminosity in this context is the energy, which is just the total power let's say, transported outward. And you see that eventually, we obviously start with 0, right? And then as we go to the core, since the fusion is happening everywhere in the core, you have more and more luminosity, but eventually here, the production of energy stops, right? And the energy is just transported outward. It's basically conserved. So the luminosity of the sun is more or less constant from these 0.30 or 0.35% of the radius all the way outward. What changes is the spectral distribution of that energy because the sun is cooler and cooler, okay? So all the energy that leaves the solar surface was created in this inner 30% here. And basically mass is just in a way the integral of the density, right? So you see that basically the more steep this increases, the more dense sun is at that point. Okay. Cool. Well, finally, this is what happens inside. And this is, again, this is something that we don't see directly. This is what theory predicts, right? We know some equations that govern how the interior of the sun should look like. We solve these equations for given boundary conditions and given constraints, and we obtain something like this. This is exactly what these people do, and some of you might even recognize that this was plotted in IDEA, right? So this is a relatively old book, right? Cool. But finally, we reach the atmosphere, and atmosphere is super amazing for us. I mean, super interesting for us, at least for me. It's because that's where the light that we see is created. Okay, and this is something that is interesting for astrophysics in general, not only for solar physics. And you probably know about this plot here, right? This plot here shows the shapes of the spectra for the stars of different spectral classes. And in this context, the spectral class basically means color, okay? And what we see here are actually the distribution of the light from blue to the red part of the spectrum for various spectral classes, and we see that it looks a little bit different, right? And the most differences that we see are these dark regions here, right? And these dark regions we call spectral lines. We see that the absence of and the number of these spectral lines and their strength changes dramatically between the spectral classes here. Does anybody know roughly why is it so? What determines the differences in the spectrum? What is the most important parameter in the atmosphere of the stars and the sun as well?
I would think composition.
Composition. That's what people thought as well. They thought, okay, the different spectral classes have different composition. Because, for example, this line here is the line of hydrogen, right? So this means that the hydrogen is absorbed heavily in, for example, atmospheres of A0 stars, which sort of makes you think, oh wow, that means that that stars of this spectral class have more hydrogen. But that's actually not true. That's not true. So another amazing astrophysicist, Cecilia Payne-Gaposchkin, actually shown that it's the temperature that determines all these things. So temperature determines what elements will be capable of absorbing at which wavelengths. Because keep in mind the following thing. I'm just going to give this example now. We're going to go through this in much more depth, but I really like this example. The fact that, so this specific line here is famous H alpha line at roughly 650 nanometers. And that spectral line is created by the absorption of the photons, which correspond to the transition from second to third level of hydrogen. Okay. We will see later how the spectral lines come to be and so on, but this is something that you more or less already know from your physics classes, etc. In order to have this absorption, you need to have hydrogen, which is excited to the second level in the first place. And it turns out that this temperature here is exactly the sweet spot. If you increase the temperature, it's so high that hydrogen atoms are ionized and they cannot absorb. While if you decrease the temperature, you will figure out that now the temperature is so low that hydrogen cannot be excited to the second level, and then absorption is again low. And then here you already see some of the problems that we are going to face when we try to interpret spectra, is that calculating the spectra is already a messy business, because you need to know a lot of this underlying microphysics that is happening there. You need to know statistical physics to see how all these things are ionized and excited. You need to know atomic physics to calculate all the probabilities of various processes. Eventually, to really solve these problems, you need to solve a lot of equations, which means you need to know numerical methods that deal with that, and so on and so on. And you need to have very good friends who work in the labs who are going to provide all the necessary atomic and molecular data for you to do these things. So I hope that during this class you'll have some time to devote to the NIST web page, where they have amazing collections of the atomic data for various spectral lines and atoms and so on, and to use them practically in some of our hands-on exercises. Okay, to strengthen this, and this is the example from the internet that we see very often, which annoys me a little bit, and I'm going to see why. And very often people like to say, okay, the photons are created in the core of the sun, and then they slowly diffuse or scatter, and then they go up. Of course, it's amazing, and it's very interesting to sketch this random bulk of the photons that are going outside, but it's a bit misleading because it sort of leaves the impression that these photons that originate in the core leave the sun intact, which is actually not true, because that would mean that we can find the information of the core from the core directly by looking at these photons. What actually happens is that the original photon suffers many absorptions and emissions on its way outward, and each of these absorptions and emissions depends on the local properties of the plasma. So finally, when the photons are emitted at the surface, they carry basically the information from the so now I told you the story. We were supposed to brainstorm this together. Okay, but let's talk about this a little bit. I now talked about absorption and emission processes. Do you know any examples of these? Like what can cause absorption of a photon? I talked previously about spectral lines. Is there anything else? Feel free to say there are only bonus points. There are no penalty points for the credit. So if you're very good, you can get extra credit, but if you say a lot of wrong stuff, we are here to learn, so don't worry about that. Can photons ionize? Yes. Yes. Yeah. Okay. So let's say I have a hydrogen atom, I have a photon of relatively high energy, it hits the hydrogen atom and it ionizes it. What happens with the photon? Does it disappear? What would you say? Or let's say, can it disappear?
No.
Why?
Because it's got to be conserved somehow.
Well, the energy has to be conserved. By energy can go there. Actually, photons are particles which are by definition not conserved. So statistical physics predicts that since photons don't have mass, their number doesn't have to be conserved. So I can create photons out of energy anytime I want, and I can transmute them into energy somehow. It can disappear. So if I have hydrogen hit by a photon with enough energy to create ionization, the photon will disappear. It can disappear. It can be completely absorbed, and the energy will be spent on the ionization process plus the kinetic energy of the ejected electron. Okay, it's something similar to photoelectric effect. Einstein got Nobel Prize too. Actually, recently I found out that Einstein did a lot of other amazing things in that paper, but that's something that we always remember. Okay, any other absorption processes? Or let's say scattering processes. Doesn't have to be absorption. In astrophysics, we like to make difference between the absorption and scattering. Do you know any scattering processes? Look through the window.
Yes, blue sky.
Mm-hmm. Yeah. The sky is blue because of what process? Rayleigh scattering. Yeah. We have a lot of similar things happening in the atmospheres of the stars and the sun. For example, cousin of Rayleigh scattering is so-called Thomson scattering, which is scattering on the free electrons, which has very nice property that it almost doesn't depend on the wavelength, so it's very easy to calculate and model. Rayleigh scattering depends strongly on the wavelength. That's why the sky is blue, right? But there are also some more complicated scatterings, right? There's Compton scattering, there's inverse Compton scattering. There's something called spectral line scattering, which is a very interesting process, which is basically just absorption immediately followed by emission. And we're going to also spend some time talking about that. So there are a lot of things that contribute to transport of the light. Okay, and ultimately these are the processes that are going to determine how the spectrum looks like. And finally, these are the processes that we need to take into account when we want to interpret the spectra that we observe. Right. And so in the end, what we detect are not the original photons created in the core, it's the photons that are emitted or lastly scattered in the atmosphere. Okay. Very good. And as I told you, we can probe the interior by observing the neutrinos, or we can look at the oscillations of the sun as whole. So sun is like some sort of gong. There's even a network of telescopes called gong, which when perturbed, it oscillates nicely. And by looking at these oscillations, you can find what happens in here. Okay, very good. So in both of these examples that we took, that we have seen before, we see only the atmosphere. The big difference is that when you look at the stars, you see integrated light over the whole atmosphere. So you can't say, okay, there is this much coming from the sunspot, there is this much coming from the pores, there is this much coming from the plage, although there are some fancy, interesting methods where you could use some modulation effects to find these. Have any of you taken any courses in stellar astrophysics or something? Do you know about, or have you heard from other sources about something called Zeeman Doppler imaging? Zeeman Doppler imaging is basically a technique which allows us to see stars with some spatial resolution. We make use of the fact that stars are rotating to see how their spectra changes, and we can infer, for example, where are the star spots, and so on and so on. But of course, in the sun, we see these things there. That's why it's very important. Okay, so basically, this was just what I wanted to say is that we see the atmosphere, and an interesting thing is that when we look at something that we call continuum, it's going to be more clear what I mean by the continuum throughout the course, but basically it's just looking at the wavelength where there are no spectral lines or any strong sources of absorption. The radiation that you see basically comes from a layer which is roughly 100 kilometers thick. When I was in undergrad, I had a professor, and she would say 1%, like this. So I almost think like 100 kilometers thick, like this. Actually, it's super, super small, 1 kilometer for the sun. But that's true. And the reason for that is because the density dramatically changes. It falls off exponentially. So you can't see the radiation from the lower regions because it's absorbed by this photosphere, as I'm going to call it, and you can't see the radiation from the regions above it because there's simply not enough material to emit the radiation. So whenever you look at a certain wavelength, at least looking at the disk, as we call it, we see radiation coming from a relatively narrow layer. It can be 100 kilometers, it can be less, it can be more, but this is basically what you see. And it looks limiting, right? Because you're looking just at this very thin eggshell, but we can make use of it because when you change the wavelength, the location of this eggshell changes. Also, when we look above the limb, which means we look at the very edges of the sun, or we somehow avoid the disk of the sun, we look from the profile of the solar atmosphere, then these problems go away and we see everything along the line of sight. And then we are integrating over much, much higher distances, and then it gives us some additional information, but also many additional problems. Okay, so this is an amazing picture, very confusing also, but I think it should be in every solar physics course. This is a confusogram, as I like to call it, which repeats in a lot of publications related to solar chromosphere mostly, which tries to show various things that are happening in the solar atmosphere. So this is like a vertical cut of the solar atmosphere, which also takes into account that solar atmosphere is not homogeneous. very often we show you these plots where you see the run of the temperature, density, and so on with height, and it would make you think, okay, things only depend on the height, that's it, the solar atmosphere is very simple. It's not. Right? We have seen it here. Like the atmosphere at this point here in the pore is going to be much different than the atmosphere in this point here, which we call penumbra of the sunspot, is going to be much different than in the quiet zone, for example. So the atmosphere, strictly speaking, changes with all three coordinates, right? It also changes with time, and we're going to see some examples even today. So let's take a look at some things here, and I'm going to mention, it's not our goal in this course to study what, for example, fibrils are, or what canopy magnetic field is, or so on and so on, but we need to touch on these in order to understand how we want to design our observations. So let's say that one of you, for example, wants to study, I don't know, the coronal loops and their connections to magnetic field in the photosphere. You need to understand how the magnetic field of the coronal loop is connected to the magnetic field of the photosphere. Then you need to see what imprint this magnetic field of the photosphere leaves in the spectra that DKIST or any other ground-based telescope can observe. And then you need to figure out how to devise your experiment, how to devise your observing proposal in order to ultimately obtain numbers for this magnetic field, and to be able to say, okay, in this point magnetic field is 1000 Gauss, in this point is 100 Gauss, in this point there is no magnetic field. Or even further, in this point is pointing upward, in this point it's horizontal, and so on. And also to say the uncertainties for this measurement are such and such. So we're going to try to go through this process during this course. I hope we will succeed. So here you can see various phenomena that is happening. I'm going to go through some of these phenomena in detail, just to illustrate that there's actually physics happening in the atmosphere of the sun. So I'm not going to go through this picture in detail, rather I'm just going to start and talk about some of the phenomena that we see, and one of the most obvious one is the granulation. Also, what I didn't mention so much is that one of your independent assignments for this course, at least for the people who are taking it to credit, is we're going to try to make a mock, or maybe not even mock, maybe a real DKIST proposal. So you should come up with an idea of something that's either interesting to you outside of your project, or maybe find something that the ground-based telescope would be useful for within your research project. So pay attention to these like physical things that I'm going to talk about here and there, and other people are going to talk about here and there, because that might help you come up with some ideas. So granulation is something that you just see, right? You take a look at the sun in high resolution, you don't have to use any specific wavelengths corresponding to spectral lines. You're going to see these, bright blobs and these dark regions in between, and these we call granules and intergranules, right? And these are, as I said, roughly 1,000 kilometers, which would be 600 miles, right? Something like that. Or speaking in terms of resolving power, a typical canonical size of a granule is 1.25 arc seconds. Okay, the whole sun is 32 arc minutes. So there is a lot of granules in the sun. Okay, and can somebody tell me why are the granules bright and intergranules dark? What physical parameter the brightness of these features depends on? Temperature, yeah. That's true, yeah. These are simply the hot regions, intergranules are the dark regions. And that's something that's immediately obvious to us. However, people study, and now I'm going to show you video. So this is video again from the Swedish Solar Telescope. It's going to be, since we are streaming from my computer to Zoom, the screen is going to be a little bit poor, but you can see, let's repeat it, that things are changing with time, right? This is basically a series of images made at one fixed wavelength that show you how the granulation is changing. And one thing that you can see is that quality of these images is not the same at each instant in time. Even if you look especially carefully, you can see that even, for example, this part of the image looks a little bit more blurry than the right part of the image. And these are the consequences of the Earth's atmosphere. So Earth's atmosphere is very complicated medium. And in order to reach the telescopes, the light that emerges from the sun needs to go through the Earth's atmosphere. And the Earth's atmosphere creates a lot of, I don't want to call them aberrations, because aberrations are usually related to the lenses, but let's say it creates a lot of disturbances in the wavefront. And we now have some numerical methods how to correct for this, and some very good tricks. But we are never ever going to achieve the ideal observing conditions that we have in the space. And one of the goals is also going to be to emphasize the differences between the space missions and ground-based missions. I like to say that DKIST is in a way going to be a space-based telescope located on ground, mainly because of the fact that once the the instruments are set up and tested, they're basically going to be sealed, and very few things will be changed by hand. Right? Typically, at the ground-based telescopes today, you have people who go to observe, and they set up things any way they like. With DKIST, mostly because it's super high-tech and super expensive, you won't be able, observers won't be able to meddle. You actually won't even go to the telescope to observe. Most of us, when we write the proposal and it's accepted, somebody else will carry out the observations and send us the things, and we maybe zoom in during the observations to see how the things are going. For space-based missions, it's even more advanced. Simply the space-based mission observes, and the data is reduced and stored somewhere online, and you just go and download it. And sometimes the data even contains the physical parameters that you need for your research. We will work with some examples of this data. We'll download some data from SDO a little bit, and a little bit more data from a space-based mission called Hinode, which is a spectropolarimeter put in space, which produces spectra and the polarization. And actually, at the end of the lecture, there is a small brainstorm using Hinode data. However, people study granulation and they come up with a plot like this one. So I'm sorry for the poor contrast, but now this is for the first time a plot of physical parameters. So this is not intensity of the light, this is not polarization of the light. These are actual velocities on the surface of the sun. And as usual, red corresponds to the positive corresponds to velocities receding from us, which means material going down. Blue is material coming up, and now you actually see that this is these are the plasma velocities, which are consistent with the picture we have of the granules, right? The warm regions are coming up, so they have to have the blue shift. The cold regions are the ones where the plasma is going down, and they have the red shift, right? So I already told you the answer for the next question, but the next question is going to be, can we obtain this sort of plot just by looking at the image of granulation? And if not, what do we need?
You need spectroscopy.
You need spectroscopy. Very good answer. Yeah, so just by looking at the picture, there is no way for us to figure out what goes up, what goes down. Maybe if we have a time series of pictures, we can figure out what goes how the things move in the plane of the sky. And actually, we're going to do an exercise in that at some point. We're going to talk about something called local correlation tracking. But for this, we need spectra. We need to see how the spectral lines are shifted to the red and the blue, and then we can get these kind of things. And relatively soon, you're going to make a plot like this yourself. You're going to download data from a publicly available space mission or some publicly available ground-based data. You will come up with a model, you will come up with your method, you will code it, and you will get a plot like this. And now, for example, from the science point of view, you could now take a look at the power spectrum of this. You could correlate. For example, you see that in the middle of the picture, the velocities are lower. That's because there we have something called plage, which has its own magnetic field, which inhibits these velocities a little bit, but not completely. So you could study the interaction between the magnetic field and the velocity, and so on and so on. So one of our goals is also we can't really tell you, listen, you need to find this for your project to be, better, but we can try and teach you how to infer these physical parameters from the data. Okay. Then we got sunspots. Sunspots are basically we know now that these are the bundles of the magnetic field that are, protruding from the photosphere, and they look very dark because they are cooler in a way, right? So of course they are not black. They look black because there's much lower intensity there, but their color, if you could observe isolated sunspots, somehow the color of the sunspot would be probably maybe reddish or orangish, something like that. The real question is, how do we know that this is because of the magnetic field, right? And we actually know it almost for 100 years. And these amazing people, whose names you probably know, so Hale, actually this course is named after Hale, right? This is Hale Collaborative Solar Physics Red course. Ellerman is famous because of element bombs, right? And Joy is well known because of Joy's law, and about Nicholson atom. Yeah, but this happened. This paper came out 101 years ago. The observations were made even before that. And what we have here is actually the application of spectroscopy to solar physics. So what these people did, and we're going to talk about this in much more detail how this works in the next classes, but basically when you do spectroscopy, you need to sacrifice one spatial coordinate for the wavelet coordinate. So usually when we look at images, we have information on X, Y distribution of intensity. When we do spectroscopy, what we do is basically we isolate radiation coming from this black line here, which we call spectrograph slit, and then we disperse it. So what we will have is the information only along this line here, so only along Y we see the variation of intensity, but we also see how intensity varies with wavelength. Okay. And here there is absorption, so distribution in wavelength is relatively flat, however there is one absorption line here. Okay. When we move to the Y locations which correspond to sunspot, we see that this line, so you can't see it here because resolution is relatively poor, but trust me, that the line splits into 3 components. And when Hale observed this, it became immediately clear that this splitting into these 3 components is something called Zeeman effect. And Zeeman, who actually got a Nobel Prize for the discovery of Zeeman effect, discovered this effect in the lab just maybe 10, 15 years before that. Okay, and this effect is basically the splitting of the energy levels in the atoms when you put them in strong magnetic field. And basically from the amount of the splitting here, you can more or less directly, but you can quantitatively infer the strength of the magnetic field. So literally just by looking to say, okay, this line is split into 3 sublines, let's call them. They are separated by this and this, this amount of angstroms. I can infer the magnetic field there. Today we have even more fancy methods which rely on the polarization of the light, but we're not going to talk about it today. But you can see it nicely here. So what we see here are the 4 different points in the solar atmosphere. So quiet sun, something like penumbra, limit between the umbra and penumbra, and umbra, which is this dark region of the sunspot. And you can see the spectra. This spectra was obtained with, the space-based telescope. And you can see that in the quiet sun, the spectral lines look like you would imagine them. Just absorption of the light at 2 different wavelengths. As you move toward more and more magnetized regions, the lines are more and more split. But of course, you don't know in advance that these regions are magnetized. From the splitting of the line, you are inferring the strength of the magnetic field. Does it make sense? Okay, we'll go into Zeeman effect further, but you probably remember from your quantum classes from like undergrad that there is this thing called Zeeman effect and it splits energy levels. Okay. And this is a picture of the sunspots. We're not going to go into it a lot, but we basically know that they are sort of dark because this strong magnetic field inhibits the convection, so the gradient of the temperature is different and the emission is simply different. So it's not our goal today to talk about the sunspots. However, we can, and now what we can do today is, in a way, we can, so here is a picture of the sunspot. What we can do today with the modern telescopes is we can take spectra of each of those points separately. and we can use them to infer magnetic field in each of the points in the sunspot. And then we can get maps of them in the same way that we have obtained the map of magnetic field before, of the velocities before. When we talked about convection, we can obtain the maps of the magnetic field now, which is really fantastic. And then there are people like, for example, Matthias Rempel from HAO, who do super realistic simulations of these sunspots, putting inside all the relevant physics. So we, on one hand, can observe these sunspots, infer their magnetic fields, and so on and so on, and then we can compare it to the observations. Okay, then if we move a little bit higher in the atmosphere, and we're going to also spend a lot of time talking about what is higher, we can see something completely different. Here is a video of something called solar prominence, which is basically a bunch of plasma, which is somehow suspended in the high layers of the solar atmosphere. And we see that the plasma is evolving with time, and eventually a part of it is, ejected, and eventually will maybe start floating toward the Earth, or so on and so on. But what I most want to focus on here is that now we see something completely different, right? The sun looks different, it's like we're looking from a different angle, and so on and so on. What would you say? What are things that are immediately obvious to you that is different between this image and, for example, this image of the sunspot? What would you say that differs in these two examples?
Scale.
Yeah, scale is definitely different, right? So there we could only see a very small chunk, and actually sunspots are maybe roughly size of 1 Earth minute or even less. Well, here we basically see a big part of the sun, right? So these observations are done with some different kind of telescope, and actually this is probably SDO, so probably this is just cut out from the whole image where we see the full solar disk. So solar telescopes also differ vastly with their not only resolving power, which mostly depends on the size, but they also depend on the context that they are used for. Some of them are used to observe the whole sun as a disk, the whole solar disk. Some of them, as Dickies, for example, are going to only look at very small chunks with very high resolution. Right? The other thing is that the surface of the sun doesn't really look like what we saw before. Of course, one part of that is because this is not much different resolution. The other part is that we are looking at significantly different wavelengths. So before we were looking mostly at the optical wavelengths, where here we are looking at ultraviolet wavelengths observed. And of course, ultraviolet, most of the ultraviolet wavelengths we can't observe from the ground, we have to observe it from the space. So this is definitely a space image. Don't get confused with color coding, right? So usually the colors that we see have nothing to do with the actual light, right? This is UV light. This is not visible. Okay, and then we can study these things in much more detail. I'm going to run through it a little bit faster, but eventually, again, by looking at the spectra of this object and polarization of the light in this object, we can, for example, infer their magnetic field structure. But then it also carries some problems, and actually, this is an example which is now significantly ahead of us, so we need to learn a lot of physics to be able to understand it. But basically, what these people show here is that we can't uniquely determine the magnetic field structure of these objects. Sometimes the physics is just so complicated that different combinations of physical parameters produce identical observables. So there are some things in the sun that we can't really know uniquely. There are ambiguous solutions by the nature of physics behind them. We'll talk a little bit about it, but that's also there's also a relatively unsolved problem. So now let's mention briefly something called solar chromosphere. So this is probably a picture from Wikipedia. And then when you go to Wikipedia, the definition is going to be something very traditional, let's say. They're going to say that chromosphere is a very thin layer which you see during the eclipse and which has these vivid colors and so on and so on. What would you say if I told you that we can look at the chromosphere not during the eclipse, but from above. So how can I look at the chromosphere, on this? What do I have to do? Do you have an idea? I'm just going to show you a picture of the chromosphere, and you're going to tell. This is again a ground-based picture of the solar chromosphere, and you can maybe recognize a sunspot here, but the rest of the picture looks completely different to what we saw before. What is the difference here between this image and previous images? Is it different sun? Is it different physical phenomena?
It's not stereo.
It's not stereo. No. Now, this looks a little bit 3D because the distribution is like this, but this is just a regular image. But what's the difference?
You have to look at different bands.
You have to look at different bands, or strictly speaking, you have to look at different wavelengths. So the observations that we make today are so narrow in wavelength that you can really isolate very specific contributors to the emissivity and opacity, I'm going to call it, which basically means you can isolate very specific absorption and emission processes. And we're going to see that by probing different wavelengths, we can probe different phenomena and different heights in the atmosphere of the sun. And hence, looking at different wavelengths, the solar atmosphere looks completely different. And there's this amazing GIF made by our colleagues here at DAN using IBIS instrument, where we have a chunk of the sun, right? But then for each of the points, we have spectra, basically. We have observations. And now this right panel shows you how we are changing through various wavelengths in the spectral line. And the left panel shows you how the image will change, right? And by tuning, and look at the range here. This is from 854.1 to 854.3. So this is 0.2 nanometers. We can resolve the light in fractions of the nanometer. So our spectral resolution here is super high, okay? And really by just changing the wavelength a little bit, so just going from here to here, which is fraction, which is 0.0 something nanometers, your image looks completely different. And that's because you are looking at the radiation coming from different layers in the atmosphere of the sun. And this is very important, and DKIST will do these observations routinely. And one of our goals that we're going to learn how to do, or actually how we won't learn how to do it, but we are learning how these instruments work, right? How the spectrographs and fabric barrel filters, things like that, what's the theory behind them and how they work, and what are the things, right? And then finally, with the DKIST, we will also be able to see the corona. So you probably know corona is this very, faint light, which is only visible during the eclipse. It's not because eclipse creates corona, it's because eclipse obstructs the disk, so we can see this much more faint radiation coming from around. But with the DKIST will work as a coronagraph in a way. But we can also see corona directly, not with the ground-based telescopes, but for example with SDO. Looking at far ultraviolet wavelengths, we can see how some parts of the corona look like. Of course, this corona up here and this corona down here are not exactly the same, but we can still, study some stuff. The main premise while I was showing all this is to say that things look different at different wavelengths. And you can even see when you look at the example of a person here, right? And this is a very dramatic example, but for me it's usually very important. It's when you look in the optical at the person, what do you see? Where does the light come from? Original. When we look at objects around us.
Reflections of the surface.
It's most of the cases reflectance of the surface. And it does depend on the properties of this, right? My sweater is green. But reflectance of this sweater depends on the properties of the sweater, but it depends on its reflective properties, right? The sweater itself is not emitting the light. Here we see the image using infrared camera. And here we actually see that, for example, glasses are obstructing the infrared light. And so they look dark. So So in a way, the glasses are like, some absorption clouds over the face, and so on. So here we literally see the emitted light by the person. And this is really, exaggerated example, but it shows why it's important to look at different wavelengths. And for example, SDO is already doing that, not by literally scanning through the wavelength. I mean, it also has one instrument that is doing that, but just by looking through different filters, you see different physics happening in the sun. And this is a very famous picture, and I just want to say that apart from talking about, of course, we won't be talking about these wavelengths because these are not available from the ground, but we'll make some analogies. We are going to be particularly interested in these first two here. And these are the plots of the velocity of the plasma and the magnetic field of the plasma. So contrary to everything else, which are direct observations, these are derived quantities. These have to be inferred from the observations using some physical model behind it. And a good chunk of our course is going to be about it. So to summarize, different wavelengths probe different regions and different phenomena and different processes. And to understand what is happening in the solar atmosphere, which is usually what our research project is connected to, we want to know the strength of the magnetic field, we want to know velocity of the plasma, we want to know how whichever of these parameters is changing with time, we need to understand processes happening there. And very often, I didn't show it here, I'm going to show it relatively soon in the next week or so. We want to measure the intensity of the light, but we also very often want to measure the polarization of the light. So DKIST is also polarimetric telescope. I think 4 out of 5 so-called first generation instruments that we're going to have we will be able to do polarimetric, not only imaging and spectroscopy. But to do this, we need to have the observations, and we need to know how our observations were created and what influenced them. So once again, our course is going to be on gathering the data, interpreting the data, and figuring out what kind of data we need to support our research idea. We'll try to use some very simple models to do some really hands-on things, like, for example, to estimate velocities, to estimate magnetic fields, to estimate temperatures, and so on, to track features on the solar surface, etc. But I will have to tell you about something more complicated ones, because solar physics is, in terms of diagnostics, is sort of advanced because of the richness of this data. So we use relatively sophisticated physical models today, and some of these will be even used by default for this DKIST efforts. And if you happen to like this topic, and I'm going to repeat this in the next class when we are all here, there are DKIST workshops happening through the year. The first introductory one was last June. Then one is happening right now. It's about image restoration, and actually Kevin, when he comes back, and he's going to give you 2 hands-on exercises at the end of January, he's going to choose some of these exercises and do them here with you so that you can get a taste of that, how the image restoration works. But we will have the other ones coming in the future talking about magnetic field estimation, coronal diagnostics, and so on and so on. So if you are into these kind of things, stay in touch with us and we'll let you know what's happening. So once again, we want to have data cubes. And here I'm showing something similar to the GIF I have shown you before, except now, instead of the intensity only, I'm also showing how different valence are polarized in different amounts. And the amount of this polarization gives us the magnetic field and the orientation of the magnetic. However, we'll have to understand a lot of physics to be able to interpret this. So what I want you to do, and the ultimate goal, is to get not only the velocity maps, but also maps of the temperature, magnetic field, and so on and so on. But since we're already running out of time, I want you to think about this image. This is a beautiful image, maybe the most famous quiet sun map ever made. It's made with the space telescope. Its dimensions are roughly 2,000 times 1,000 pixels, so there's 2 million pixels here. And what I'm plotting here is only the intensity of the light at this wavelength. So for Thursday, think a bit from the physics that you know by now. Don't overdo it, just think a bit casually. What kind of physical parameters could you infer only from the intensity? And we will pick up here, we'll discuss this briefly, I'll show you example of the data, and we'll then move on. And next class we're going to talk about physical quantities that we measure. So it will be maybe a little bit boring. We'll have to talk about fluxes, intensities, number of photons, some theories related to that, and so on and so on. But we'll try to relate what theory predicts, what we can calculate from the sun, to the things that we measure in our instruments. And we'll see how the size of the telescopes, how the sampling and these things determine what we actually measure, the numbers that we get. And we'll look at some examples. Questions, comments? Yes.
At one point you said something, I'm sorry, I didn't quite catch it. You said that when you go to do spectroscopy, you sacrifice, I think it was spatial resolution. Is that what you were saying?
No. I said we sacrifice one spatial coordinate. So we'll go into this more in a bit, but it's simple as this. Our detectors are always 2D, or our detectors are cameras, right? I can't record a three-dimensional information simultaneously in any way. So usually we are used to images, because image is something which is very intuitive for us. We look at the world around us, our eyes are constantly creating some images, right? And the camera in the telescope works in a very similar fashion to eye. You have a lens which collects the light, you put the camera in the focal plane. Of course, there are many mirrors usually in the telescope, so it's never in the primary, but you can imagine that it's in the primary, it doesn't matter. You record the image that is created in the focal plane. And it's very simple, right? However, if you want to make this kind of data cube, as is the one here, here our information is obviously three-dimensional. In which sense it's three-dimensional? Well, we have information about space, about x and y intensity, but also we have the dependency of the intensity on the wavelength. So if you were to imagine this, this would be like a 3D cube, where you have intensity depending on the three coordinates. And of course, I cannot simultaneously record the 3D information on my 2D detector. So what I can do, and the way that this image is made, is you have a filter which is very, very narrow. So you made an image on one wavelength, then another wavelength, then another wavelength, then another wavelength. So strictly speaking, these different wavelengths are also made in different times. But then you can do something different. You can use a slit. And what slit is going to do, it's going to isolate one column of your image, and it's going to disperse that column. So you're going to get information on one coordinate and wavelength. You're going to record that. Then you're going to move your slit. You're going to take the next column, and so on and so on. So now you're going to have different, for example, x coordinates in different moments of time. So you are now sacrificing one spatial coordinate to get the wavelength coordinate, okay? And so on and so on. In theory, and in the case we'll have one instrument like this, we can have something which is called IFU, and IFU is a generic name for integral field unit, where you usually devise an observation in such a way that you cut out a very small region from the field of view of your telescope, and then you have a very complicated set of optical elements, which basically creates copies of that region at different wavelengths and put them next to each other on the camera. So you use your camera to have a lot of small images at various wavelengths simultaneously. So that's currently the only way where we can have 3D information. We'll talk about it further when we in the first part of the course. We'll actually see how it is, not literally how it is done, but conceptually we'll try to understand what is there, and we'll actually, since we have the data cubes, we'll be able to sort of de-slice them back and to see how they look like. More questions? Any questions from the online participants? Okay, sounds like we're good. So see you Thursday, same time. See you, students. Stay here for 5 minutes so that we can get to know each other a little bit. Bye.